Hey YouTube, in this video we're going to be introducing the concept of the algebra of functions. And essentially what this is just the same thing as the algebra of real numbers, say, except for dealing with functions as its elements. So let's say, for instance, here we have two functions here, f of x, and we'll say f of x is equal to 2x. And we say we have another function, g of x, and g of x is this other linear function, x minus 1. What do I want to do with these two things? Well, maybe I want to add them or subtract them or multiply or divide these things. And what we have is some function of another quantity here, x. And so we can just deal with these just as we do with kind of real numbers. So what we're going to notice here is that over here in this diagram we have for each function f of x equals 2x and g of x equals x minus 1. We have four different operations that we tend to do when we work with function notation. And we say we could add, subtract, multiply, and divide two expressions in x. So starting with this notation, we'd say f plus g of x. What I want everybody to understand is this f plus g of x is kind of like me saying some h of x, which h of x would just be equal to the sum of f of x and g of x. And so when we say f plus g of x, this doesn't mean that we're going to distribute the x. It doesn't mean anything other than the name of this function is f plus g of x, and it's got that name because we took f of x plus g of x to get it. So we could say that there's this sum of two functions, we call it f plus g of x, and we say that it really just means the same thing as f of x plus g of x. And so what I want everybody to see here is that this f of x, really all they've done is they substituted in the 2x for the f of x. And we say for g of x here, we'll just drop this in parentheses, its expression is x minus 1. So we'd say 2x plus x minus 1, we end up with, well, 3 total x's minus 1. And this is what we're referring to as our new function. And I will say that this new function, really its name is f plus g of x, but we could say it's some new function h of x that is really the sum of these two things. So with all of these that you're seeing here, f minus g of x, you'll notice it's f of x minus g of x. And all we'll do is we'll plug in our f of x rule and our g of x rule. And in this case, it's very important that we plug in g of x in parentheses because we'd have to distribute the negative throughout. But basically, we're just going to insert their rules for their functions here. So looking at the product of these two things, we say f times g of x is f of x times g of x. So we get 2x times x minus 1, which in turn would give us 2x squared minus 2x. And then my favorite of all of the operations with two functions, combinations, we say is f over g of x because quite literally, this means that we have f of x over g of x, and that's the same thing as 2x over x minus 1. So now a couple of things I'll say on this one. One is you're done once you get to this point, as long as nothing simplifies top and bottom. And also this right here. They've stated that the domain can be all x values such that x cannot be 1. And the reasoning behind this is because setting our denominator equal to 0, we solve for the x value here and we get 1 for value. That would be the x value that would cause us to divide by 0. So that being said, what I would like to be doing or do is combine some functions that I've defined here. So we say f of x and g of x. So for checkpoint 2, it says f of x is x minus 5, g of x is x squared minus 1. We want to find each of the following functions. So we're going to be finding f plus g, f minus g, f times g, and f over g, which are 4 operators that we use with real numbers as well. But afterwards, we're going to determine the domain for each function. So let's start with f plus g of x. We notice that f of x equals x minus 5 and g of x equals x squared minus 1. So when we say f plus g of x, the first thing I'm going to do is I'm going to encourage everybody to rewrite this as what it truly means, which is f of x plus g of x. Now once we've done this, excuse me, I'm going to drop in blank parentheses for each of these quantities, but I know that f of x is the same thing as x minus 5. So we're going to put in an x minus 5 as a substitution. And I know that our g of x is x squared minus 1. So for this right here, we would say that I get x minus 5 plus x squared minus 1. We could drop the parentheses. Looks like we get x squared. Looks like 1 total x. And we say negative 5 and negative 1 give us a negative 6. So this function right here, just to be clear, is our f plus g of x function. And it's what we got when we added these two together. Now in terms of the domain, I am going to make a comment here that we're never going to divide by 0 here. We don't have any expressions in x in a denominator. And we don't have any expressions in x on the inside of an even root. So what we're going to get is a negative infinity to infinity domain, right? Well, here's the thing. We have to check on this. So what I mean by check on this is we have to understand something about the combinations of two functions. So under a sum, difference, product, or a quotient of two functions, we say letting f and g be these two functions, then the sum, difference, product, or quotient are functions whose domains are the set of all real numbers common to the domains of f and g. So if we use capital DF here to represent the domain of f and DG to represent the domain of g, what this basically is saying is that the domain of this new function f plus g or f minus g or f times g or f over g of x is really where these two domains overlap with one another. They have to have an intersection of those two. So what I want to point out is that this original function here, x minus 5, is a line. It's a linear function. So its domain is negative infinity to infinity. And so we're also going to find the domain of g of x, which its parent function is x squared, which means it's a quadratic thing, which has a domain of negative infinity to infinity. We would say that the graph of this would have a domain of negative infinity to infinity since it has no restrictions, and because these two domains overlap on all real numbers there, negative infinity to infinity. So we say here is our domain. Now looking at f minus g, one important thing to realize here is that just like with real numbers, when we have a difference of two functions, the order in which we do this is going to matter. In this particular instance, we have f of x minus g of x, where f of x is again this x minus 5 that we'll substitute in, and g of x was our x squared minus 1. So the importance here is that we say I've got a negative in front of an entire set of parentheses. So what I'm going to do is I'm going to start by distributing that negative throughout and make this a positive 1. And then I'm going to combine like terms. So I would have negative x squared plus an x, and a negative 5 and a positive 1 would be minus 4. So this would be our new function. We would give it a name. We'd say this is f minus g of x. So now looking at our last two here, we say f times g of x. We're going to start by rewriting this as to what it truly means. We say f of x times g of x. So in this case, we're going to end up with x minus 5 times x squared minus 1, which means we're going to end up having to FOIL here. So we get x times x squared is x cubed, x times a negative 1 is negative x. Negative 5 times x squared is negative 5x squared. And then last but not least, negative 5 times a negative 1 is a positive 5. So our final function here, fg of x, is x cubed minus 5x squared minus x plus 5 when written in standard form. And so last but not least, we'll take a look at D here, and then we'll talk about the domain of these last two that I just found. So D, okay, so f over g of x. What we need to do here is rewrite this as f of x over g of x, and I'll tell you what, we're as good as done as soon as we get to this point. We say f of x is x minus 5, and then g of x is x squared minus 1. So now, this is our final function, right? Well, here's the thing. I noticed that I could factor the bottom. And I'm going to want to make sure I do this. Now, I want to comment on this. Nothing cancels on top and bottom, but that doesn't mean that it won't. So we need to check for common factors. And also, we said that the domain of this would be restricted. It couldn't allow us to have 0 in the denominator. We can't allow ourselves to do this. So if that's the case, what we're going to do is we're going to set it equal to 0 and solve it. And so here's the other benefit to having factored it. You've already got this set up so that we can say, well, then x plus 1 equals 0, or x minus 1 equals 0 if these multiply out to be 0. So x equaling 1 or negative 1 is going to cause us to have a 0 in the denominator. So the domain of this last function here is where these two domains overlap, and also not allowed to be at 1 or negative 1. So the domain of this right here, we could say, is all real numbers such that x is not allowed to be plus or minus 1 if we're not writing it in interval notation. So now the only thing I wanted to comment on these last two here where we were finding the product and the difference of these two functions is the domain. We would say that the domain on both of those is going to be all real numbers, or at negative infinity to infinity, just because of the fact that they're polynomials. And that's basically all I needed to say about those. So last but not least, we'll take a look at this last set here. We say f of x is this square root function x minus 3, and g of x is another square root function x plus 1. And we're asked to find each of the following f plus g and then the domain of f plus g. So let's just start with f plus g. You know, what we get is something pretty interesting here. We say f of x plus g of x is what this really means. And in this case, we're going to say, well, f of x, I'm just going to go ahead and substitute this directly, and we say is the square root of x minus 3 plus g of x, which is the square root of x plus 1. So now we're asked to find the domain of this, and it's like, well, you know, what do we do here? Do we set what's in here greater than or equal to 0, or what's in here greater than or equal to 0, or do we do this with both? Or do we find the overlap of those, or what is it that we're finding here? And what I can say is it's really truly the overlap of the domains of the original two. Remember, it's the intersection of their domains for which they're defined. So I know that this is a square root graph. I'm just going to kind of conceive of this a little bit here. My original square root graph does this, My square root graph shifted to the right 3 would now be at 3 here and would open to the right. So its domain, I would say its domain is 3 to infinity. We're just going to list the domains of each of these original functions first. Now x plus 1, the square root of that there, it would be shifted left 1. This is a very poor sketch here, but we could say its domain is negative 1 to infinity. So if we said, well, what's the domain of this composite function here that we just found that it's done? I mean, we can't do anything more with that. That's our f plus g of x. What's the domain? I would say it's the intersection of these two sets. So again, one way to do this is to use a graph to do it. We'd say 0, here's negative 1, and we'll say that this is 3 just because I said so. So 1 is here, and the other one is way out here and goes to the right. We could see that the intersection of these two would be where these two overlap right here. So we would say the domain of this overall composite function, or not composite, rather combination of two functions, is this right here because that is where their two domains overlap. So we say the overlap of the domains. Cheers.